Well, hello everybody. Once again, my name's Christopher Collison, and this is the second video on quantum mechanics for the course CHMP 442 at RIT. And we're going to look today at a little bit more information about why there was a need for quantum mechanics. And we're really going to be sort of answering this question of what provoked that need for its development. So, moving on, we start by thinking back about 120 years or so. And it turns out that as science progresses, more experiments are done and we start to try to understand what's going on in the world. And there were these three observations that were confusing for scientists at the time. And I talked in the last video about how quantum mechanics solves some of this confusion. But these observations could not be addressed with classical mechanics of the time. And these problems were really molecular or atomic phenomena in nature. So we're going to go through these today: black body radiation, the photoelectric effect, and atomic line spectra. So let's turn our attention first to black body radiation. And so I write here that this provided the biggest question of validity of classical mechanics, and you'll see why shortly, because the theory of the day had no way of actually describing what was being measured in reality. And so we start by thinking of a heating element, and we've all seen these rings, electric rings on the hob, and on our cookers, on our stoves. And the idea is you turn up the temperature, and we've seen that as you turn up to high on your stove, the color of those rings goes red. At low temperatures, so just overall at low temperatures, the element simply appears black. But as higher temperatures take place, that black body, if you will, starts to glow red, then white, then blue. So there's a color change, and we have a frequency distribution. Frequency again means color here. So we have a distribution of colors of light that's emitted by any hot body, and that frequency distribution changes with the temperature. So here is the theory of the day, and I plotted this in Microsoft Excel, and the theory of the day is given by this equation up here. This is called the Rayleigh-Jeans law. And what we find here is, if we look at the y-axis, this is a relative intensity of radiation. So we're not going to worry too much about the numbers in here. What we're going to think about is the shape of the graphs. We can also look at the equation. So on the y-axis, this function, this relative intensity, is proportional to the temperature, T here. So what that means is that, for example, this expression is a function of wavelength in here. If we pick a certain wavelength, 2000 nanometer, for example, if we increase the temperature, we go from black to red to green to blue, then what happens is this intensity of radiation goes up. So that intensity is proportional to the temperature in this equation. So what else? We also note from this equation that there is a list of constants in the first part. So we're going to not worry so much about those constants. We've got the Boltzmann constant. We've got c being the speed of light. But what we're going to turn our attention to is that this theory of the day has the wavelength squared on the bottom in the denominator. So that intensity, that relative intensity, is inversely proportional to the square of the wavelength. So what this means is, at low wavelengths, what we find is, of course, that this relative intensity starts to go up. And at high wavelengths, when the denominator gets larger in here, then the intensity starts to go down. So what are the problems with this particular theory? And I think some of you will be able to see fairly shortly what happens. I'll look at some real data. The actual data, by the way, follows this magenta curve, and this makes some sense, right? Because when we move towards the ultraviolet, if the Rayleigh-Jeans law was correct, then we would expect to see a huge intensity of radiation that would come from our black body, and that simply didn't happen. So Max Planck was one of the pioneers that turned his attention to this particular problem. And before we jump into that, here's some data that actually comes from the textbook. And I bring this up because in the textbook, for example, they're using on the x-axis the frequency in here. So, of course, that's inversely proportional to the wavelength. So we've flipped the axis around. So this is the same data. We basically now see that as when the frequency is low, that means the wavelength is high. We have a pretty good fit down at these low frequencies, at these high wavelengths. But again, like I showed in the previous graph, what happens is the theory kind of shows that this the theoretical curve just goes shooting up, and in reality what happens is the curve kind of comes back down again, and this is what we see in reality. So you can read the figure caption. There's also some stuff in the figure caption here talking about how they describe units in these graphs. So the units per second, and also the 10 to the 14 is actually embedded here in the label for the units of the axis. So I wanted to draw your attention to that very quickly. But let's come back to what Planck is putting forward as a solution to this problem. So let's think about what happens in any solid. We have a crystal lattice, and we heat up that particular material. As we heat up any material, these atoms move around more quickly. This leads to this thing called incandescence, which means that light is given off by that black body, and we expect the frequency to increase. We expect as we heat it up that the colors will shift towards the blue. But as I've mentioned already, the intensity of the blue light does not increase as much as the classical balls on the springs would have us believe. So Planck supposed, and he comes up with this idea that there must be a certain threshold of energy that must be attained by these vibrating atoms before some light, in fact, before a packet of light could be released. So for UV light to be emitted, he's putting forward this idea that there'd be a large amount of energy, a large threshold of energy that would have to kind of come together before a UV piece of light could be emitted. And similarly, for red light, a lower energy threshold would be required. The next couple of slides, there's a lot of text. I'm going to try to explain what I'm trying to write in this text. So there's a lot of text in this slide, but basically Planck is putting forward this idea that energy is equal to h times nu. So nu again is the frequency, and h is this Planck's constant that we now assign to Max Planck's name. So the way I look at this, and this is kind of what all this text is saying, is that when we think about red incandescence, so for this hot body, we might think that maybe all these atoms are vibrating. Let's think about vibrating pairs of atoms. The way I look at it is perhaps to get 3 pairs of vibrating atoms to kind of resonate together. That will bring about a certain packet of energy. With only 3 vibrating pairs, when they're vibrating in resonance, that's probability wise, that's fairly easy to attain, and so it's easy to release this red light. However, if we think of a new energy threshold, let's say, for example, we need 8 vibrating pairs of atoms, and everything's kind of going on in this sort of random nature. But if we get 8 vibrating pairs that have to come together in order for a larger packet of energy to release, that becomes harder. So a larger packet of energy would be UV light, and this kind of idea, I think, is what Planck may have been thinking, in that when we have a higher frequency, bluer light, we have to have some way of describing how much more energy is going to be in that single packet of light that needs to be released. So I kind of go through in here, a couple of different ways in this slide and the next as to how I think about this. And none of this may be technically and fully accurate, but I like to think about things in a sort of qualitative way so that we can kind of get our heads around them before we might dive into the theory associated with that. So bottom line is, as we add heat, there's a certain probability for releasing now what we know as a photon. When a red photon is released, it carries less energy than when a UV photon is released. So it's easier to get that to happen. And therefore, we're going to expect that as we go to in the Rayleigh-Jeans law, if we look at the graphs, it's going to be harder to actually release those UV photons. And that's why that graph kind of turns back down again. So I'm going to sort of pause there. You can pause the video and have a look at my words. There's more words on this particular slide, so you can kind of, whatever you need to do to kind of get your head around this, that's okay. So you can pause this if you'd like. But the key features here, the key things are that really down here, however you look at it, it turns out that the black body radiation curve can only be understood if quantization exists. What does quantization mean? It means that energy comes in packets. So, and UV packets have much more energy than red packets, and therefore it's less likely for that energy to be released in a blue photon compared to a red photon, and that's why that curve drops back down. So we can only start to fit this data when we start to think about E is equal to H nu, and that's what this last bullet says down here. So let's come back to, again, a fairly busy slide. I actually put back up here. Here's the equation that we started with. This is the Rayleigh-Jeans theory, but Max Planck is proposing that energy should be quantized. He's postulated that electromagnetic energy, that's light, did not follow the classical description, but could only oscillate or be emitted in discrete packets of energy proportional to the frequency. That's this idea of quantization. At the time, this was an ad hoc assumption. So it was an assumption that was needed to address this particular experiment. There was no precedent for this, but it's somewhat justified in that it gave the right answer. So here again, we look at our equation, and we recognize that because the frequency times the wavelength is equal to the speed of light, we can substitute hc over lambda. We can substitute the c over lambda for the frequency in here. So we've got actually a c over lambda in this particular equation. Let's move those back out of the way. But the point here is we've got this, it's this packet energy, h nu, that's included in this part of the equation. I'm recognizing at this point that we're not going to spend any time really in this course thinking about this black body radiation equation, But it turns out that if I plot this particular equation in Excel, I get back something that models pretty much exactly the actual data that would be observed on your stove. So the point here is that when we include this sort of E equals H nu term, what happens is Planck's equation now fits very closely. It actually overlaps this sort of magenta curve in here, and so this approach worked. Planck's H nu, this is an H nu in here, later had another application, so stay with me. We'll come back to that, and H nu shows up a lot in this course. So that's what kind of quantization is based upon. So now, having looked at black body radiation, which I think is a little bit more challenging for chemists, we'll gradually move towards atomic spectra. But next up, we're going to look at the photoelectric effect. And first of all, I'm going to explain the experiment. So again, what's happening in this experiment is we've got this little circle in here, and this circle represents a vacuum chamber. And in that vacuum chamber, what we have is a metal in here, and this electrode is a metal, perhaps something like potassium. And what happens is we're going to shine some light through the glass walls of this chamber, or some light that's shone onto that metal. Of course, light, how can light vary, right? We can vary the intensity of the light. We can also change the color of the light, the frequency of the light. And what we've also got in here, we have another electrode. And this sort of dotted line in here represents the positively charged electrode. And what that means is when this light hits the metal, we're going to get electrons that are emitted, and they are accelerated towards that positively charged electrode. There's a couple of configurations to the electric circuit in here. In the first configuration, we've got this switch in here, and the switch basically connects us with a fixed voltage in here. So we've got a voltage source, a fixed voltage in here, and we also have a galvanometer, and a galvanometer simply measures current, which is the number of electrons flowing. So what you could do with this part of the experiment is you can shine light onto your metal, and you could measure the number of electrons that are generated as a function of that light intensity or color, and that shows up as a current on this galvanometer. Another thing that we can do is if we flip the switch, so if we come back in over here the other direction, what we can also do is we can this is a rheostat. This is a variable resistor in here, so that allows us to change this voltage on the left hand side of the circuit, and so we would break the switch here. We'd apply different voltages such that actually the current would read 0. So when we do that, if we know the resistance and we know the voltage, then we actually vary the voltage and change that voltage to a point that we're getting 0 current. And what that tells us is basically, that tells us when we got 0 current, it tells us that the excess kinetic energy of these electrons, so these electrons are flying out here, when we get 0 current, there's enough kinetic energy in those electrons so that those electrons will reach the circuit independently, and it's balanced by the counter voltage that we're putting in over here in this sort of rheostat. This sort of left-hand side of the experiment here basically allows us to measure the kinetic energy of those electrons that are given off. So, you know, I'm describing the experiment here. The important part here is to think about what Einstein did and how he interpreted this experiment. And that's the key feature that we want to take forward. So if you're interested in how this experiment was run, go take a look. If my explanation is not fully clear and you're interested, go take a look at that. But this is sort of the physics and the circuitry. Let's actually look at the experimental data. And, in this experimental data, what we find is that the kinetic energy is on this y-axis. And the frequency of the light is shown on the x-axis. And this is what the data showed us, right? So over the next few slides, I'm going to talk about the key features to this graph, and I'm going to tie it to the key outcomes of the experiment and why that ties in with quantum mechanics. So first up, if you remember this diagram, right, maybe we look at the features. There's a certain threshold frequency here. We'll look at this shortly. And there's a sort of a linear slope up here, right? So, of note from that experiment, no electrons were emitted until that threshold frequency was reached. Okay, so let's take a look here. Again, now I've sort of identified a few more features. Over on the right hand side of this graph, we've got UV light. On the left hand side of the graph, we've got red light. We kind of also now know from E equals h nu that red light has less energy in each of these packets, or photons, as we're going to find out that they're called. So the key part here is that there's no kinetic energy. There's no electrons actually released until we've reached this threshold frequency. That's the first point of note. The second point of note is that if we go higher than the threshold frequency, these electrons are ejected with an excess of kinetic energy. So we also, by the way, can think about that as this kinetic energy comes because this excess kinetic energy comes because there's a certain ionization energy of an electron in an atom. If you put in more energy, then you're going to give that excess energy to the electron after it's left the atom. So with hindsight, we can kind of start to interpret this already. This is what Einstein did. So if higher than the threshold frequency, then these electrons are ejected with an excess kinetic energy. The key feature here is that when the scientists turned up the intensity of the light, we're putting more energy into the system by increasing the intensity of that light, right? More energy with higher light intensity. But it turns out that had no impact on the excess kinetic energy. It only turned out that this excess kinetic energy was proportional to the wavelength of light. So again, this is this proportionality that's seen here in this linear graph, right? So the key point here is that frequency was proportional to the excess kinetic energy, and the intensity of the light made no difference. Going to this third bullet here, when the experiment was done at a threshold frequency, or at a frequency that was higher than the threshold frequency, right? So that means sort of somewhere in here, right? It was the current, not the excess kinetic energy, but it was the current that was dependent on the intensity of the light. So it seems that the more, the greater the intensity, i.e. the more photons that were put in, the more electrons that would be generated. The last point in here is that below that threshold, of course, there was no current that would ever flow. So the only rational interpretation of the day, and this sort of happened at the same kind of time as the black body radiation, the only rational interpretation here is that one photon, one packet, right, would give one electron. More of those packets, more of those photons would mean that more electrons would be released, and therefore more current would be generated. And we already know this, right? That electrons in atoms have these fixed ionization energies for all of the elements in the periodic table. So if we look at potassium, it's relatively easy to pull one of those electrons out. So we shine light, and that if that light has enough packet energy, E equals h nu is enough, then we can kick out an electron. So when the photon energy is greater than that ionization energy, we get electrons out. If there's more energy in the photon than is needed to pull that electron out, then that excess energy would go into the kinetic energy, which would zing that electron off towards the positive electrode. So the key point here is that from this experiment, it looked like photons were indeed particles. Next up, we're going to look at atomic line spectra. Again, all of this stuff coming at around the same time. And so in your textbook, there's a figure 1.6 in here. And this is an emission spectrum of the hydrogen atom in the visible and the near ultraviolet region, showing this particular line structure. So Balmer, this is in 1885, discovered this series of lines, but what was determined was an empirical relationship. So what does that mean? There was an equation, so we have an equation here that describes the positions of those lines. 1 over the wavelength in here, so the wavelength is the position of that line. 1 over the position of that line in wavelength terms was equal to this constant here, later called the Rydberg constant, multiplied by 1 over 2 squared minus 1 over n squared, where n was some integer. And this was unusual. Why an integer? And nobody knew where this equation came from. Nobody really knew why it worked. They only knew that it empirically described the positions of these lines. So the Rydberg constant, here we go. Oh, interesting. There's 9 significant figures here. It's pretty accurate. So what can we take away from this? So these lines are sharp. They're not continuous, right? They're very sharp peaks. And that's why, in fact, this Rydberg constant can be determined with 9 significant figures of accuracy. We also know that each element has a characteristic spectrum. So I'm describing this atomic line spectra description as a problem, because the empirical equation worked, but nobody really understood where that Rydberg constant came from, and really what the relationship with this integer 1 over this n squared, integer comes from. What's the significance of that? So a theory of the structure of atoms would have to explain these 2 ideas. This is another plot from the textbook, and this is basically saying that the frequency, or 1 over the wavelength, if you will, is proportional to 1 over this n squared term. So we'll come back to this later, but the key thing here is that these were the 3 observations. There was no escape. We needed to have a new way of looking at things, and what came next, this was the confusion. What came next was quantum mechanics, which allowed us to deal with that confusion. And I'm going to go into some of the history of that, kind of 10-minute review of the history of quantum mechanics in the next lecture. So thank you for listening, and we'll see you in the next lecture.